The limit comparison test comes in handy when I know I want to compare to a series but I have the wrong inequality relationship. It goes like this. Suppose sigma a sub n and sigma b sub n are series with positive terms. If the limit as n approaches infinity of a sub n over b sub n is equal to c, where c is a positive finite number. I'm going to pause right there. Positive means it's not zero. Finite means the answer is not infinity. So if the limit of the ratio a sub n over b sub n is equal to a positive finite number, then either both series converge or both series diverge. We'll prove this and then we'll get to some exercises. Let lowercase m and uppercase m be positive numbers such that c is between lowercase m and uppercase m. We have that the limit of a sub n over b sub n is equal to c, which means we can say that the ratio a sub n over b sub n is close to c for large n. And because of that, there exists uppercase n, which is an integer, such that a sub n over b sub n is between lowercase m and uppercase m when lowercase n is larger than uppercase n. Let's unpack that a little bit, and I'm going to use a diagram. We've said that c is between lowercase m and uppercase m, and so what I have here is an n-axis and then a y-axis, because I didn't know what else to call it, and then a horizontal line at c, and then I guess it's a ray, but and then a horizontal line at lowercase m and a horizontal line at uppercase m, c being between lowercase m and uppercase m. Now what we've got is that the ratio a sub n to b sub n has a limit as n approaches infinity of c, which means that at some point, let's suppose that a is smaller. It doesn't matter for this whether a is smaller or bigger than b, but at some point the ratio is going to end up being closer to c than either m or n, because the limit of the ratio is c. So that at some point, we'll call that point uppercase n, and now what we're saying is for any indices to the right of this uppercase n, the green curve is closer to the purple curve than either of the blue curves is. And that's what this inequality says here. The ratio a sub n over b sub n is between lowercase m and uppercase m when lowercase n is larger than uppercase n. Going back to the inequality, we can clear a fraction and end up with lowercase m times b sub n is less than a sub n, which in turn is less than uppercase m times b sub n when lowercase n is greater than uppercase n. We're going to use that to draw some conclusions. If sigma b sub n converges, so does sigma uppercase m times b sub n, because multiplying by a finite number does not affect convergence. Then we have, from the compound inequality, a sub n is less than a converging series uppercase m times b sub n. Thus, the sum of a sub n converges by part 1 of the comparison test. On the other hand, if sigma b sub n diverges, so does sigma lowercase m times b sub n, and in this case now I have a sub n is larger than a diverging series. So sigma a sub n diverges, this time by part 2 of the comparison test. And that concludes our proof. Now I need to tell you about two special cases. These are cases in which the limit is 0 or infinity for the limit comparison test. If we form our ratio and find that the limit as n approaches infinity of a sub n over b sub n is equal to 0, And if sigma b sub n converges, then sigma a sub n also converges. The way I think of this is that if sigma b sub n converges, then it's a finite number. And if we form a ratio of a sub n to b sub n, and that limit turns out to be 0, then a sub n converges probably faster for us to end up with a limit of 0 if sigma b sub n converges. On the flip side, if the limit as n approaches infinity of a sub n over b sub n is equal to infinity, and if sigma b sub n diverges, then sigma a sub n also diverges. Again, the way I understand this is that if the denominator series blows up to infinity, but then the ratio also blows up to infinity, then a sub n has to blow up to infinity. Note that in both of these cases, we actually have to know something about the denominator series b sub n. So now it matters which one we put in the denominator.